Hey pre-calculus friends, here we are in section 8.2. We're going to be talking about algebraic vectors. Our notes and vocabulary today start off by giving us a way to kind of represent a vector as an ordered pair. And so I think an example would be helpful to understand what this section is saying. So let's look at an example. So suppose we have this vector here that I have highlighted in pink, and the vector has a beginning point and an end point. And so that's what P1 and P2 refer to. So let this be the initial point. This is our P1 and this is our P2, being the terminal point. The ordered pair for this vector, so let's call this, I can call it P1, P2 vector. I'm going to call it vector A, just so we can kind of think about it as a singular thing, but this is totally fine way of writing it as a vector. The ordered pair that represents this vector will be the difference between the x's and the difference between the y's. But when we find that difference, we need to make sure that the terminal value, so for me it's 4, 8, the terminal x term is what I'm subtracting the initial x term from, and the terminal y term is what I'm subtracting the initial y term from. So the way I would write this is I would use an ordered pair, but I'm going to actually, instead of using parentheses, I'm going to use what looks like greater than less than signs, kind of like I don't know, an arrow-like parentheses. I don't know if it has a name, but so this would be the ordered pair that I'd use to refer to this would be 3, 4. Does that kind of make sense? And if you think about it, if you think about the displacement is 3 units in one direction and 4 units in the next direction. Let me see if I have that right. Is it 3, 4? 4 minus 1, 8 minus 4, 3, 4. So the displacement of the point would be 3 units this way and 4 units this way, even though it doesn't look like it. My graph isn't drawn to scale. Does that make sense? So this ordered pair is what I'd use to refer to this vector. And of course, the magnitude, which we know is the length of the vector, we can get from, and that's what this is here, the distance formula. So we remember the distance formula, the distance between those 2 points, or I should write it the way we're dealing with it here, the magnitude of A, I'll try to be neater, the magnitude of A is going to be just the distance of that, or the length of that segment, and we know what that is. That's going to be the difference between the x values squared, so that's going to be 3 squared, 4 minus 1 squared, 8 minus 4 squared, which is going to be 16, or 4 squared 16, and we know 9 squared plus 16 is going to be the square root of 25. We would get 5 as the length or the magnitude of this vector. Okay, so that's what we kind of get the power to do, and being able to translate vectors into this ordered pair gives us the power to do some cool vector operations. So let's say vector A was was referenced by this ordered pair a sub 1, a sub 2, and vector B was referenced by b sub 1, b sub 2. Then there's some real number k. Here are the things that we get to do. We can do addition. If we are adding vectors, we can add the same parts of the components of their ordered pair. So a sub 1 plus b sub 1, comma a sub 2 plus b sub 2 would be the new vector, the addition, the sum of these two vectors together. Subtraction, similarly so, we will be subtracting the quote unquote, I'm going to call it the x component, you know what I mean, but the x-like components of these two vectors, and then the y-like components. And look at the order. Notice that if A is first, we're adding, well, addition's a little bit different because it's, we've got the commutative property, but not so with subtraction. So we got to be careful. If it's if it's vector A minus vector B, you want to make sure that you're doing A minus B in each of those, a sub 1 minus b sub 1, a sub 2 minus b sub 2. And then scalar multiplication is pretty cool. If you're multiplying vector A by a scalar k, you're going to multiply each component of that vector by k, each of those parts. I keep calling it components because you might realize, remember when we talked about components in the last section, we talked about the idea that going this way is like a horizontal component, and then going this way, let me use a different color, is the vertical component. And if you notice, that's what we end up with when we talk about the vector. We end up with the ordered pair that refers to the vector. So the ordered pair is, I know this orange doesn't look like 3, but it's 3, and this green doesn't look like 4, but it's 3, 4. Make sense? So that's really the component parts of the vector. Okay, let's look at a couple other things. One more vocabulary term we need to look at is the unit vector. The unit vector is considered a vector with a length of 1, with a magnitude of 1. So the unit vector, as we have it here, can be aligned with the x-axis or the y-axis. When we talk about the unit vector in reference to the x-axis, a horizontal unit vector, we refer to that as I vector. And when we have a vertical vector, the unit vector, that's J. And this is how you would write it down. It kind of makes sense. If you think about I in reference to its beginning point and end point here, and we think about the difference between the x values and the difference between the y values, you'll see the y values are the same, so we get 0, and the x values are, the difference between them would be 1 step. So this 1, 0 makes sense as the ordered pair we're going to use to refer to the I vector. And the j vector, similarly, we can talk about the initial point and the terminal point, and the difference between the x values being 0 and the difference between the y values being 1. Okay, with that, let's get to some practice. Here in example 1, we're going to write the ordered pair that represents the vector from point x, which is at -3, +5, let's say somewhere here, and point y, which is at +4, let's say here, and -2. All right, so we've got these 2 points. I'm going to write them down so we can keep in mind what their values are. And now what we want to do with this information is we want to find the magnitude and the ordered pair. So that represents this. So you remember from our rule, we know that we need to consider what the direction is. Since the vector goes from x to y, in that way, we're going to consider y.2 and x.1, and we remember to figure out what this vector is in terms of the ordered pair writing that we just learned about. We're going to subtract the second term, the y value, the x value of the second term. No, we're going to subtract the first term from the second term, right? You know what I mean? The terminal, from the terminal term, we're going to subtract the other one. All right, you know what I'm talking about. So the displacement basically for in the x direction from -3 to +4 is 7. That's ultimately what we're figuring out here. So 4 minus that, and then from -2 -5, this displacement is going to be kind of like in the negative direction, because in this way, notice that our vector is kind of going in the positive x value but negative y. So it makes sense that when we do -2 - 5, we get a -7. Y'all with me? I hope so. I hope that made sense. So that's the first part. We wrote it as an ordered pair. Then we've got to find the magnitude. What I like about the magnitude is that the magnitude, since we've already found the difference between the x's and the y's, we know that the magnitude is going to just be the distance formula, which requires us to find the distance between the x and y, and then square those, add them up, then take the square root. So we know that this would be 4 minus a -3, 7 quantity squared, and then -2 - 5 plus -7 quantity squared, and the square root, that's our distance. And then so now we get 49, and 49 is 98. We get the square root of 98, which we recognize is going to be pretty close to 100. 9.8 or 9.9 is going to be pretty close to 10. 9.8 or 9.9 might be a good approximation. If we wanted the exact answer, however, we would reckon the fact that 49 times 2 gives me that 98, and then I can write this as 7 square root of 2 if we wanted the exact value. But if we wanted to approximate it, I should probably grab a calculator to confirm, but it's going to be something like 9.8 or even 9.9, really, really close to 10. Square root of 100 is 10, and square root of 98 has to be very close to that. Hey pre-calculus students, we are in section 8.3. We're going to be talking about vectors in three-dimensional space. So before we even get into our notes fully, we need to kind of consider what does three-dimensional space look like when we're talking about the coordinate plane. So basically we started off with, we started off really with x-axis or the x number line, and then we added to it the y number line or the y-axis. And here we go. We recognize that the right side of the x-axis is positive, the left side negative. This part of the y-axis is positive, this part negative. And I'm going to highlight accordingly. So this is the positive part. Let's say the positive is going to be in green there, and this is the positive part of the y-axis, right? And we know the negative part will be down for y-axis and to the left for the x-axis. And the reason why I'm pointing that out is because I want you to think about what's happening here. So the x and y axes literally are flattened, have been flattened and turned onto this red axis here. So what I'd like to show you is that this is the negative part of the y-axis, and this is the positive part of the y-axis. All right. And the positive part of the x-axis is running out towards us, and the negative part of the x-axis is running behind us. So if you took this and you laid it down on a page, in a way you can say that we are kind of talking about it on a sheet of paper, and oriented it like this red coordinate plane is, that would be the XY plane. And then so what we get added to it, and if we were to draw it here, we'd think about this thing coming out and coming back as the z-axis, but that's not how we write it mathematically. I kind of wish we did, but that's not how we do it mathematically. Mathematically, this is the orientation that we'd set up. So z is usually up, and x and y laid like this. So as you would think, or as you probably already guessed, the positive portion of the z-axis is up, and the negative portion of the z-axis is down. And so this is how we can graph things that are three-dimensional. And we'll be talking a little bit about that during this lesson, most definitely. So you may have thought about the idea of what it would look like to graph a point on the in the coordinate space, in three space. Okay, so if we're talking about that, we would definitely be dealing with, instead of an ordered pair but an ordered triple. So let's say we wanted to graph the point 2, 3, 4. If we wanted to graph this point, we have to recognize that 2 refers to the location on the x-axis, 3 refers to location on the y-axis, and 4 refers to location on the z-axis. So how do we draw such a thing? Well, we're actually going to be using parallelograms to do so. So the first thing we need to do is locate positive 2 on the x-axis, and then we need to locate positive 3 on the y-axis. And instead of drawing a point, we're going to kind of draw a parallelogram here, such that the sides are parallel to the axes that we're drawing. So you kind of got to get a sense of this three-dimensional business here. So let me see if I can make this look like what I'm trying to do. So I'm going to start here, and I have the luxury of having the app that's kind of altering my little lines here. So that's the first thing. And so now what I've located here is the point 2, 3, 2, 3, 0, because I haven't yet moved it up or down to talk about its, to represent its z position. So from here, I need to now find 4 on the z-axis. Positive 4 would be here, 1, 2, 3, 4. And so now I'm going to finish off this drawing by actually making somewhat of a cube. All right, so you guys see what I'm doing here. Let's try to make that a little bit better. You guys kind of get what I'm doing. Every time I draw a line, I'm going to make the lines parallel to the axes that I'm drawing over. Hopefully this is looking like something to you guys. Somebody said a hot mess, but I'm trying, chablitos. Okay, so then this point here, let's think about it. We went over 2, up 3, and then up to Z, up here to 4. And so that's the point. This point here is our point 2, 3, 4. That's how we'd graph it, okay? So now that we can talk about graphing in 3 space, graphing in 3D with these ordered triples, we can also talk about vectors that have that are in space, right? You can talk about vectors that are now shooting out in maybe this direction here or something like that. So now if we can talk about those vectors, we should be able to do the same thing that we did with the vectors when we were dealing with 2 space, right? Flat on the coordinate plane. We were able to use the points to refer to the vector as an ordered pair. Here we'll do an ordered triple. So that's what's happening here. So it says, suppose you have this point is the initial point of a vector and this point is the terminal point, then the ordered triple that represents it, very, very similar to what we did before, is going to be the difference between the x values, the y values, and the z values respectively, and that will be your ordered triple. And then the magnitude really is going to be quite similar. It's going to be the square of each of these values added together, then we'll take the square root. So that's really the principle of what we're going to be talking about in this section. So in this example, we are asked to locate the following point. So we remember this is x, y, z, just like in alphabetical order. The first thing we'll do is locate negative x, which we know is going to be going away from us. So I'm going to locate that 1, 2, 3, 4, negative 4, that is, which is there. And then we're going to locate positive 3 on the y-axis, which is here. So now let me use a gray pen to demonstrate where this is going to go. So it's going to be something like this and like that. So if I was just graphing this in the coordinate plane XY, that's where my point would be at this gray dot. But I'm not doing that. I'm also going to be taking it up to 2. And so I'll put a little mark here. And we know that we're going to continue drawing the rectangles or the parallelograms parallel to the base to create the box that's going to give me my location. Let me go ahead and try that line again. So I'm going to bring this out a little bit further. All right, let's try the whole thing again. All right, then down, then over. Let's make it parallel, something like that. And then we'll do the same thing here. Down, then over, and this is the point. This is that location. Do you guys see the three-dimensional figure we have to kind of draw in order to find that one point? And that point is the point negative 4, 3, 2. So we've located it on the coordinate in 3 space, I should say. I keep wanting to say the coordinate plane, but that's not right. In example 2, we're supposed to write the ordered triple that represents the vector from x to y. So we remember that the rule told us in order to represent this as an ordered triple, we're going to find the difference, but we're going to start with the end point and subtract the initial point ordered pair. So we'll start like this. 4 minus 5 is going to give me negative 1. So that's for the x value, and then negative 5 minus a minus 3 will give me a negative 2, and then finally 6 minus 2 will give me a 4. And so that's really it. That's all we needed to do. If we were to find the magnitude, we would square each of these, add them up, and then take the square root. Entomology. Okay, so entomology is the study of insects, and entomologists often use time-lapse photography to study the flying behavior of bees. They have discovered that worker honeybees let other workers know about new sources of food by rapidly vibrating their wings and performing a dance. Researchers have been able to create three-dimensional models using vectors to represent the flying behavior of bees. So, in reference to this little passage, we are supposing that the flight of a honeybee pass through point 033 and then point 504, in which in which each unit represents a meter. What is the magnitude of the displacement of the bee experienced in traveling from these 2 points? All right, so we can kind of look at this as the initial point and this is the terminal point and kind of come up with a ordered triple to represent the situation. So let's call this point A, let's call this point B, and we can classify or write down a different way of looking at this vector AB as the difference between, so 5 minus 0 is 5, and then 0 minus 3 is negative 3, and then 4 minus 3 is 1. So this is the way we could look at the vector. And we remember to find the magnitude of such a vector, we're just going to take the square root of the sum. Let me see if I can do that again. Take the square root of the sum of the squares of each of these component parts. So 5 squared is going to be 25 plus negative 3 squared, which is 9 plus 1. And so 25 plus 9 plus 1 is going to be 35. So the answer is going to be the square root of 35. That's the magnitude, and that's in meters as they mentioned. And so that's going to be somewhere close to 6. It's going to be like 5.8, 5.9. Okay? I think 5.8 actually might be closer. Okay, 5.9. So here we're asked to find an ordered triple that represents 3 times the vector p minus 2 times the vector p. If p, vector p, is given or represented by the ordered triple 3, 0, 4, and vector q is represented by the ordered triple 2, 1, negative 1. All right, so this is going to be a lot like we did last time. So 3 times p would be 3 times kind of like that scalar multiplication we did before. So I'm just going to write it out like that, and then we're going to subtract from that 2 times vector q, which can be written like this. And so when I do that, it really is just a little distributive property. So I end up with 9 minus 0, 12, and then I'm going to subtract from that this vector 4, 2, would that be 2? That's an interesting thought. I think I'm just going to go with the positive. 4, 2, and negative 2. Notice I did not quite distribute through with the negative. I was trying to figure that out for myself, but what I was thinking is I'm just going to leave the negative here and then deal with it later. I hope that made sense. I hope you saw what my little struggle was. And then so now I'm going to do the subtraction, and here's what our final answer is going to be. So 3 times vector p minus 2 times vector q can be written as this ordered triple. 9 minus 4 is 5, 0 minus 2 is negative 2, and finally 12 minus a minus 2 is a positive 14. In example 5, we're to write vector AB as the sum of unit vectors for A beginning at 5, 10, negative 3, and B being at negative 1, 4, and negative 2. Well, first, I think the first thing we should probably do is write this vector as an ordered triple. And so we would be doing B minus A. So we end up with negative 6, negative 6, 4 minus that, and then negative 2 minus that is going to be a positive 1. So this is what we end up with as the ordered triple representation of that. Now what we're going to do is recognize that each of these really is going to give me what my unit vectors are. So remember, my unit vector for the horizontal was I, and then my unit vector for the vertical was J. And so that's going to stay the same. When I'm thinking about the X direction, it's I. When I'm thinking about the Y direction, it's J. But when I'm thinking about the Z direction, it would be K. All right, so now we can write this as negative 6i, last time I forgot my vector signs, plus, or I guess we could say minus, minus 6j, and then plus k, vector k. And so that about sums it up for us. Hopefully this made sense and the three-dimensional drawing won't be too tricky. All right, guys, look forward to talking to you soon. Bye-bye.